It is my great pleasure to introduce today John Black from University of Colorado, Boulder, and he's going to tell us about some recent attacks on MD5.
Okay, thanks, Christine. As Christine said, my talk is about MD5, and my name is John Black. I don't really know what to assume about this audience, so when I wrote my talk, I sort of assumed that you had some exposure to some security primitives, block ciphers, and hash functions, and so forth, but that you're not intimately familiar with how they work and the recent attacks that have been mounted against them, and so forth. So is that a fair assumption? Yes? Okay. So for those experts in the audience, I apologize in advance for boring you for the first bit of the talk. I was told I can make this interactive if I wanted to, so I'm going to. Let's start with a question. So here's the setting. You have this great scientific discovery. You have figured out how to factor products of large primes in constant time, polynomial time, or that P doesn't equal NP, and you have a proof. Something like this. Really, really big deal. But you're not really ready to reveal this to the world yet, because maybe there's some problems, or you have to flesh out some more details, and so forth. And at the same time, you don't want to sit on it for 2 months while you work out the details, because somebody else might come up with the same idea, beat you to it, and you get 0 credit. So what do you do? So that's my question to you. What do you do? Mike?
Well, you take one-way hash of it and put it in the personal.
Very good. Okay, so yeah, so you could hash it, meaning use a cryptographic hash function, take the digest, the output, and publish it in the New York Times or something, right? And the idea is that you're not revealing anything about the actual contents of your result because you only published the hash, and these things are supposed to be one way. And also, you've committed. You can't change. Why can't you then change later on your document to claim you actually knew more once somebody else publishes something extra? Because the hash would change almost certainly. Not necessarily, right? If there's a collision, it wouldn't change. But almost certainly, if you make any change at all, you're going to get a different digest. And it should be hard, according to the security of these functions, to do that. So I'll go over more detail of what I just said in just a minute. The old way that you would do this is you would mail yourself a copy of it and then use the postmark as your timestamp, right? But there's some physical properties with the security of this. This other one, assuming that the hash function is good, doesn't really have any problems. Okay, so hash functions. That's just one application of many, many applications for these things. But what are these things? They're functions that we think of something large down to something small. But of course, it could be something small to something small. They take any input, any string of any size, and they output a digest or a hash of their input that has some fixed length. Okay. Ones you may have heard of before are things like MD4 and MD5 and SHA-0 and SHA-1 and so forth. All right, so to get a little bit more into the details, when I say hash functions throughout this whole talk, I mean the cryptographic kind. I don't mean the kind where you just multiply it by some number, take it mod of prime, and that's for data dictionary kind of applications. I don't mean universal hash families. I mean cryptographic hash functions. As I just said, they take any string of any length down to some fixed length. So here I'm saying 0, 1 to the star means strings of any length, and the output R, the range of the function, is k bits. So we'll use k conventionally today to talk about the size of the digest, how big it is. And typical output sizes are 128 for MD4 and MD5, 160 for SHA-0, SHA-1, 192, 256, 512, and so forth. These are the typical hash function output sizes. They have a few requirements. They should be simple, portable, fast to compute. Obviously, something that takes 3 hours to hash, 10K document isn't going to be as appealing as something that does it lickety-split. So all of these things have always been designed to be friendly to computers, run well on commodity hardware, be portable, and so forth. And also, we have some security properties that we need as well. And we'll talk about that in a moment. So here are the security definitions. And you'll notice I put the word definitions into quotes. So maybe you've seen this before, or you can think about it now. But these definitions really aren't good definitions. And let's read through them. These are the ones you'll find in your typical crypto texts. And oftentimes they forget the quote marks. They actually write them down as real definitions, when in fact they're not very good definitions. So here are the terms that, that people care about with the security of hash functions. Number one, collision resistance. Okay, collision resistance means you can't find two distinct inputs that hash to the same output. If you do, that's called a collision. Inversion resistance. Given an output, given a hash digest, you can't find any input that hashes to that output. And finally, second preimage resistance, which is if you're given an input-output pair, in other words, you're given a document and its hash, you can't find a distinct separate document that also produces the same hash function, same hash value. Okay, so open it up. Why are these really not good definitions? Christina. Okay, how about in the back? Exactly. What does this word mean, computationally infeasible? How do we define that? Okay, so the typical definition for computationally infeasible is as follows. There does not exist a program that runs in polynomial time that can solve this problem. Okay? So let's pick on collision resistance, since that's the thing we're going to focus on today. Collision resistance, putting this into more exact terms, would say there does not exist a program which can output A and B distinct strings that have the same hash. Okay. If we define things that way, are any of these functions collision resistant? Why not? Yeah, it's just purely impossible, right? So all of these functions compress large strings down to small strings. By the pigeonhole principle, there must exist a collision, because there are more inputs than there are outputs. So if there exists a collision, you can't make a statement like no program can output a collision. There does exist a program, the one that simply prints out a collision, right? It prints out two strings. So there does exist a program. We don't know what it is. And unfortunately, there is no set of definitions that properly captures the intuition that we want to when we say something like a hash function is secure. So all of this operates in sort of a non-mathematical, non-rigorous way when we say we're looking for collisions in a hash function. They definitely exist, we just don't know what they are, and we have to find them essentially by ad hoc methods. Okay. Nonetheless, I think it's clear intuitively what this means. We would very much like to find two distinct inputs to SHA-1 that produce the same output. And today I'm going to talk specifically about MD5. In MD5, we want two inputs that produce the same output. And more on that in a moment. So if we have a good hash function, it should act random. And what I mean by random, a perfect random function would work as follows. Imagine a table where down the left-hand side, you write down every possible string. So it's an infinite length table. We start out with the empty string, then 0, then 1, then 0, 0, 0, 1, 1, 0, 1, 1, and so forth, all strings. And on the right side, we have k-bit outputs, the digest for each of the left-hand column strings. The right-hand column should be filled in with k random bits, independently and uniformly selected from the set of all k-bit strings. Okay? There should be no interdependence. In particular, you shouldn't see properties like correlations between inputs and outputs. So for example, and this is definitely what we try and achieve with hash functions like MD5 and SHA-1. So for example, if you run MD5 on these two strings, as I've shown here below, MD5 sum is a typical Unix utility. So if you run it on the string high there, you get this first hash function digest, this first hash. And if you write it on ho there, which is only 2 bits different in the ASCII, it looks completely different, right? It looks like completely unrelated. Certainly flipping 2 bits in the input doesn't just flip 2 bits in the output. And that's certainly what you would expect from a random function, and is a definite requirement on these kinds of hash functions. Okay, so this is already just recapping the solution we've already talked about for an application of a hash function used for timestamping, establishing time on something without revealing the content. You may have seen hash functions used for digital signatures, because digital signatures are a public key operation. They're slow. And so you can't give them gigantic inputs because they'd be really slow. So we always hash down the input and then sign the digest, right? It's called the hash then sign paradigm, and if you've taken a crypto class, you've seen this to death already. There are lots and lots of more applications of these hash functions. Here's a couple. All right. So the problem is that if you were to just take a function, a random function, from 0, 1 star to 0, 1 k, it's not going to have a compact description. It's going to really be an infinite length table. But we can't do that. It's not practical. We have to come up with something that can be compactly described by an algorithm. You have to be able to write down in C something that's no more than 2 to the 20, 2 to the 30, 2 to the 40 bits in length. 2 to the 40 would already be an extremely long program. So we can only look at programs that have a nice compact description, or they won't be simple, fast to compute, and portable. And this limits us to somewhat. But they shouldn't be something too simple, like just take the last 128 bits of the input and output that. That's not a good hash function. It's something that should feel random. Once again, this is a very fuzzy concept. What does it mean to feel random? So this is the way almost every hash function that we use is built. We build them out of a compression function. Okay? So a compression function is another hash function, but it doesn't take all length strings. It takes very specific inputs. The compression function listed here is called f, and it takes two inputs, an n-bit input and a k-bit input, and it outputs k bits. So it compresses n plus k bits down to k bits. Okay? And these things are designed by hand by the hash function designer. So you've got a compression function. Now you need an initial value, and here, and it's going to be k bits. So this is an arbitrary k-bit initial value called the IV for initial value. And this one's a palindrome. It is the IV used in MD5, in fact. So it's 128 bits, the one I've listed here. And then finally, once you have the initial value, you have the compression function, you then iterate it using Merkle-Damgård. And Merkle-Damgård works like this. So here's our friend f again, the compression function. As you can see, it takes n and k bits on the input, smashes them down, and k bits comes out. The IV is on the left of the picture, and then this value that comes out of the compressionist function is called the chaining value, because we then chain that into the next k-bit input for the next compression. So that's how Merkle-Damgård works. You just break the message you want to hash, the input you want to hash, into n-bit chunks. You stick the IV in the first chunk into the first compression function, out comes the chaining value, and you just keep doing that. The next chunk of n bits goes into the compression function with the chaining value, and you get a new chaining value, and you iterate this until the end, until you've absorbed all of the message bits of m, and the last chaining value becomes the hash digest for that message. Any questions at all? You've seen this before? About 5 people are nodding. Okay. The cool thing about using the Merkle-Damgård paradigm is that all you have to do is prove that the compression function is collision resistant. Sometimes this proof means a lot of smart people try and they can't find a collision, but if you can convince yourself that the compression function f is collision resistant, that you can't find collisions in any reasonable way, then you automatically get the entire iterated compression function. An iterated hash function is collision resistant. So this is nice because it allows you to focus just on building good compression functions instead of looking at the entire iterated hash function, which can be a lot more work, a lot harder to get your mind around. This is the first hash function. It was called Rabin's hash after Michael Rabin, who's a Turing Award winner. He did this way, way back. It's 30 years ago now. And he excuse me, used a block cipher that you've probably studied before called DES. And his approach was to just take the message blocks as 56-bit chunks and feed them into the key input of DES. The chaining value was the block input and the block output for DES. So you can build a hash function out of a block cipher. Now this isn't actually used because for inversion resistance, where we have an output and we're trying to find an input, there are meet-in-the-middle attacks. Using some feed forwards and so forth, other wires, you can make this much stronger. And in fact, there are lots and lots of ways to make hash functions out of block ciphers. But we won't. That's not the topic of the talk today. Okay, so the strength of the hash function is based on the strength of the compression function. So you have to build good compression functions. If you build them by hand and you have good confidence that they're collision resistant, you automatically get that the iterated hash will be collision resistant as well. All of the hash function attacks that have occurred over the last several decades have always focused on that compression function, because it's also true that if you break the compression function, you'll break the iterated hash. So while it's a good place to invest your ingenuity when designing compression functions, it's also a good place to invest your ingenuity when attacking them. And people have broken MD4, a guy named Hans Dobertin, who just passed away actually 2 months ago, broke MD4 back in 1996. And here, when I say break, I mean found collisions. There's other properties we're not going to talk about today. It's all about collision finding. Okay, so he found a collision in the MD4 compression function and then was able to find collisions in the overall hash function. MD5 is an improvement on MD4. So MD4 had 3 rounds. MD5 has 4 rounds. We'll see a little bit more about MD5 in a minute. But it was known and felt by Rivest that he needed to increase the strength of MD4, so he created MD5. The whole family of MD functions produces 128-bit outputs, 128-bit digests. MD5 is the only one to survive the 1990s. There were some attacks we'll see in a minute, but no collisions had been found through the 90s. And because it had lasted for so long, it was still quite widely used and is still quite widely used because we have legacy applications which use it. And as you all know, as software people, you can't just change an algorithm overnight and expect the world to adopt it, right? There are widespread deployment issues that you have to worry about, and update issues and so forth. So MD5 is still quite widely used. MD4 is still quite widely used too. Who in here has used rsync before? Okay, a couple people. So that uses MD4 still. And MD4, you can find collisions by hand now. Okay, so the first attacks on MD5 came in the 90s. De Boer and Balslers found a free start collision on the compression function of MD5. By free start, I mean that they found a message and a chaining value, and then a different message and a different chaining value, such that the outputs from the hash function, from the compression function, collided. Now, this does not give you a compression. This does not give you a collision in the overall iterated hash, because you've got a mismatch on the chaining value, and you need the chaining value to be the same. A few years later, Hans Dobertin found a collision for a fixed IV, a fixed chaining value. So here CV is the same as CV. Message blocks are different, as they must be, and there's a collision. However, the chaining value he used, which although it was fixed, was not the MD5 IV. So once again, he had collisions for a different IV other than the one specified by MD5. Getting close to a collision, but no success yet. At that point, Dobertin went dark on us, and he wouldn't publish any more stuff. He worked for the German equivalent of the NSA, and people think maybe someone put some pressure on him to stop publishing his results. It may be that he had collisions into the full MD5, but nobody had any more results after this on MD5 for many, many years. But already people were getting worried enough to start migrating away from it at this time. Okay, enter February 2004. I was on the crypto program committee. Crypto is one of the biggest conferences in all of computer security or in cryptography. And the program committee receives papers and evaluates them and so forth. And we received this submission from a woman named Xiaoyun Wang from Shandong University in China. Nobody had ever heard of her before, at least on the PC. And she had co-authors too, but she was the first author. And the paper purported to have found a collision in MD5, which would be the hugest result for years in cryptography. Unfortunately, we passed this paper around. It was almost illegible. It had been faxed in. It looked like it had first been copied onto crepe paper, then crumpled up, then flattened, and then faxed in. You couldn't read the paper. I mean, you could barely make it out. The description was unintelligible to most of us. But when you're evaluating a paper to see if it contains an MD5 collision, it's very easy to come up with accept or reject. What do? You type in the 2 inputs and see if they collide under MD5. That's really the litmus test for such a paper. So dutifully, one of the PC members typed in M and M prime into MD5, hashed them, and out came 2 different digests. No collision. So that made enough sense to everybody, right? Somebody we've never heard of thinks that she's discovered some sort of collision, just clearly confused about the whole thing, and we rejected the paper. So 4 months later, Zhao Wang decides to get a visa, come to the United States, to Santa Barbara, and attend the crypto conference, sit down with one of the people at the conference, and figure out why her paper was rejected. Well, it turned out that in the Chinese translation of Bruce Schneier's book, the endianness was wrong, and she had used the wrong IV. Her attack allows you to use any IV. So knowing this, she called China middle of the night, had her colleagues go right to work, fix the endianness problem, compute through the night. By the next morning, she had an actual attack on MD5, an actual collision, and it was verified by several people at the conference, and that night there was a rump session and she announced her results. So it was quite a shock to the community that this person who we never had heard of before had just found one of the, had achieved one of the biggest results we've had in many, many years. And it turned out when people talked to her more and more that she'd actually been working with these functions for quite a long time and thinking about them for quite a long time. More about that in a few minutes. So here it is. Here is the first MD5 collision that's ever been found. It's a 1024-bit message M. And now I'll show you M prime. So you may not see it, but there's a little prime that just appeared by the M. So here's how M prime differs from M. It only differs in 6 spots. In fact, it only differs in 6 bits. If you look at how you should replace the existing message with the new message, you're only flipping a bit. So the 8 goes to a 0, which is a flip of the high bit. And in fact, they're all flips of the high bits. Sometimes you're turning them off, sometimes you're turning them on. 7 goes to F, that's turning it on. F goes to 7, that's turning it off. And the rest are all turning it off. Okay? So only a 6-bit Hamming distance between M and M prime. She announced this at the rump session. By the way, these two things both hash to the same value, and this value is here. She announced this at the rump session with no details as to how she figured this out. And people were, of course, clamoring for details. Add to that the fact that she spoke almost no English whatsoever. In a sense, you think it'd be frustrating, but in a sense, it was exciting because it was like this big mystery. Like, where did this come from, and how does it work, and so forth. And it took us over a year to actually figure out the crucial details, and we still don't know everything about how the technique works. This is to date still the only way we know how to find MD5 collisions. All MD5 collisions we know of, and now we have millions of them that we know of, they always vary this way. They differ in exactly these 6 bits. Nobody knows any other collisions other than these. Okay? We've gotten very good at producing them faster and faster and faster, but no other ways to produce them other than to vary these 6 bits. Okay, so what her attack does is it finds a 2-block collision. So in MD5, we have a 512-bit message chunk that we feed into the top arrow and a 128-bit chaining value that follows along these bottom arrows. So all her attack does is it finds 2 512-bit blocks, M1 and M2, and it finds a different set of 2 blocks, M1 prime and M2 prime, and the same chaining value, and produces an output that's equal. It produces a collision. The nice thing is that the chaining value that you put in at the first part of this collision is the same, and it's arbitrary. Okay? So not only can you put in the MD5 IV, the one that I showed you a few slides back that was palindromic, you can put any value you like in there. And then the techniques, the attack, will then find you an M1, M2, 1024 bits, and an M1 prime, M2 prime, a different 1024 bits that will collide under 2 iterations of the MD5 compression function. So in some sense, that's very nice. It's very powerful because it allows you to choose any IV. In another sense, it's not so powerful because it really just produces 2 1024-bit chunks of garbage that happen to collide. How can that be applied? We'll look at that in a little later. Okay, so it would take a long, long time to go through the attack and how it works in detail. I'll give you the main ideas, and if you have more questions, I'll list on a slide later on a place where you can find our paper, which gives a lot more details and explains step by step how things work. So we're going to start off looking at the internals of the MD5 compression function. And I won't look at the detailed internals because that would take, once again, a long time. But I'll give you a sketch of how it works. So here's the compression function in the lower right-hand corner. It takes in 512 bits. It breaks those into 16 chunks of 32 bits each. So the compression function works on 32-bit things. And that's because at the time Rivest designed it, that was a safe size for computers to be fast on. Now maybe 64 is a little more appropriate. The chaining value is 128 bits. We break it into 4 chunks of 32 bits. Okay? So now it's operating only on 32-bit objects. And here's the compression function. You run 64 steps of this algorithm shown on the top box. And the outputs are written as Q0 through Q63. And those are called the step values. The step values are critical to the attack. You do all kinds of weird stuff on them. In fact, this is how hash functions are built. Do lots of weird stuff on things. You put them through this phi function, where phi in the first round, and a round is first 16 steps, next 16 steps, there are 4 rounds. You put them through this phi function. The first round, the first 16 steps, is indicated on the lower box. You do this x and y, or not x and z. The next 16 steps you compute with the next function and so forth. Okay? So there are these dedicated Boolean functions, 4 of them, 1 for each round. Then, up here back in the top box again, you do this to the first of the 3 step values. You add in the 4th. Add here means addition modulo 2 to the 32. You add in w sub I, where w sub I is one of those message chunks that's scheduled according to some simple algorithm. You add in y sub I, which is just a constant that depends on the round. And these constants are the decimal expansions of sine of 1 and sine of 2. And I mean sine like the curve, from trigonometry. Anybody guess why Rivest chose to use the decimal expansion of the sine of the integers from 1 to 64 for the constants? You'll see this in a lot of designs of cryptographic primitives. They'll use the expansion of e, or pi, decimals of pi. Here we're using sine. The idea is to get something that's pseudo-random, that looks pretty arbitrary and jumbled up, but also to try to reassure people who are the suspicious type, as most paranoid cryptographers are, that he didn't carefully choose constants in order to make backdoors in the algorithm. Okay? It'd be really hard to find, a function that's natural like sine is, and engineer its decimals to behave a certain way to create a backdoor. So this is supposed to be an assurance that there are no backdoors. Those are the yi constants. The triple less than sign is, as usual, left-handed circular rotation by SI bits, where SI is once again looked up in a table, a bunch of arbitrary numbers. So we're evaluating a Boolean function, or a 32-bit logical function. We're doing additions. We're doing additions by constants. We're adding in some of the message bytes. We're shifting things around. Then we're adding in another thing, jumbling up a bunch of stuff. That produces the next step value. So from Q's -4, -3, -2, -1, we get Q0. And then always using the previous 4, we get the next one, and so forth, until we achieve Q sub 63. Any questions on this? You don't have to understand this intimately to get the gist of the attack.
How can it be decimal digits? Do you represent them in binary coded decimal?
Yeah. So
okay.
yeah. So actually, I mean, I probably misspoke when I said decimal. What you do is you take the binary representation of sine of 1, and then convert that to a hex string of 32 bits and use that as the constant string. I guess the representation is not important. Okay. You seed the Q values with the chaining value that comes into the hash function. You do your 64 steps, and then to finish, you add back in the initial chaining value to the final values you got. You append those together, and that's the output chaining value. Okay? So that's MD5's compression in a nutshell. It actually runs very, very quickly because all the things we're doing, like adding mod 2 to 32, shifting things, doing ands, ors, and nots, are all very efficiently done on a 32-bit processor, 64-bit processor. So this is a very fast function, even to do it 64 times for every message block you absorb. All right, so you probably didn't completely absorb all that. One way to synopsize is just say there are 4 rounds. Each round has 16 steps, total 64 steps, and the step values are key to the attack, which is what we're going to talk about next. And they're called Q0 to Q63, and these are 32-bit values. Okay? So the properties of the step values are what matter for the attack. Now, recall that Wong's attack is aiming to produce 2 inputs, both of which are 1024 bits. That means M1 and M2, which are both 512-bit chunks, M1 prime and M2 prime. Okay, so as I said before, M1, M2 always differs from M1 prime, M2 prime in 6 exact bit positions. That's fixed. There's no playing with that. So we don't focus on M1, M2, and M1 prime, M2 prime. We focus on finding M1, M2, because from that you automatically flip those 6 bits and you've got the other one. Okay? So ignore the prime values. Those are automatically given to you once you have the unprimed values. Secondly, the attack for M1 is exactly the same as the attack for M2. It's just a different list of conditions that we have to satisfy. So the algorithm stays the same. So let's just focus only on M1. Let's just look at how to find M1. The same attack will apply to M2, to the second block. And you automatically get M1 prime from M1. You automatically get M2 prime from M2. Okay? So if you look at Wong's paper, it has these tables, these very intimidating looking tables with hundreds of characters with very specific values and so forth. And it takes a long time to extend, especially when she first published the attack, to figure out what these mean, because it wasn't really obvious at all. I'll tell you kind of at a high level what these tables mean. So here's the start of the table for the differential path, which is what's being described, for the first block attack on MD5. What it's saying is it's saying that in order to get a collision, you need, this first line says, on the third step, SI, the shift value, is going to be 22, and the difference, which is on the right-hand side, is a blank box. So there's still no difference. And that's because none of the message bytes with a flipped bit has yet been involved. As long as none of the flipped bits is involved, then you're not going to get any difference between the 2 hash functions. And this is telling you the difference on the step value between the hash on M1, versus the step value on the hash of M1 prime. So up to the third step, there's no difference. That's why the box is blank. Now, the next time on step 4, you'll see that there's the 5th column is delta W sub I. It's showing you that now one of the flipped bits is actually coming into play, 2 to the 31. That's the high bit of one of the words. And that causes the step value, Q sub 4, to be different in a bunch of places, namely in the 7th through the 22nd bit, and then minus 23 means it's actually a bit that's gone away. Okay? So there are these huge tables, and these tables keep tracking the difference in the step values between M1 and M1 prime, and that's what that right-hand column is doing all the way down. So what she's done is she's built a table which says, if I vary M and M prime in a certain way, and then I compute MD5 in parallel on both of them, the difference between the intermediate values is going to vary by this much. Now it's down to here, now it's out to here. Now these bits are different, now these bits are different, and so forth. At the end of the table, if you're looking for a collision, what should be the difference? What should be the difference remember the step values eventually turn into the output, right? It should be another empty box. Now, it won't be for the M1, because remember, we get halfway there with M1, then we have to do M2. But at the end of the M2 table, finally, all those differences in the right-hand column evaporate to nothing, and you've got a collision. Where did these tables come from? We don't know. Even to this date, we don't know. Now, I talked to somebody who knows her fairly well, and apparently she dreamt them up. Did not use a computer to find these differentials. I cannot even begin to express how complicated it is to come up with something like this out of thin air. According to my friend Arjen Lenster, who's talked quite extensively to Xiaoyun Wang, she has been sleeping with these hash functions under her pillow for 10 years. She knows the personality of Q7 bracket 15 intimately. She knows these hash functions better than she knows herself. I mean, this woman is, completely absorbed and consumed by these things until she finally broke them. So this is not something where somebody was just kind of a genius and walked up and went, oh yeah, here's a collision. This is somebody who's put 10 years of nonstop, tireless effort into these things, and then burst onto the world scene. We don't know how to generate more of these tables. People have tried, and people have tried using computers to do it. And the best other differential paths that people have come up with for MD4 are still not as good as the one she's done by hand. Okay, so still, like I just said, this is the only set of tables, the only differential path that is known for MD5. And all the collisions that we know of follow exactly this differential. And we now know many millions of collisions. If you just take two message blocks that differ by those 6 crucial bits, you're not going to get a collision with overwhelming probability. So what you do to do the attack is you pick any message block you like. And then you have to check for conditions. I'm running a little bit behind on time, so I'll probably start going a bit faster. 15 minutes left. So there's this long list of conditions that the step values all must satisfy. And for M1, there are 290 of them. And these are simple Boolean conditions like the bit here has to match the bit over there. This bit has to always be 0. This bit must be 1. This bit must be the opposite of that bit. Things like this. Things you can check very quickly.
Where did these conditions
They are also in the paper in a separate table.
So they're just...
Yes. So first you have the differential path. If you follow that path, you are guaranteed a collision. However, if you choose just 2 arbitrary messages that differ by those 6 bits, they're not going to follow the path. So now you start twiddling the bits to get them to follow the path.
But again, we don't know how she got.
The conditions are much more easy to understand the logic for. Once you have the differential path, you could say, all right, the tables immediately imply that that bit must be a 0 at that point. Otherwise, you will not follow this path. So you can do pretty simple inferences. And in fact, all the progress that's been made in speeding up these attacks, including the paper that I wrote, has to do with finding more conditions that can be easily satisfied. But nobody's figured out how to do other differential paths. That's completely opaque. No one understands how she did it, other than just by thinking them up. So she gave these conditions in the paper as well. 290 of them on the first block, 310 on the second block. And for the first round, first 16 steps, it's actually easy to satisfy almost all of the 290 conditions on the first block and 310 on the second block. And her techniques allow you to get all the way down such that there are only 37 remaining conditions on the first block and 30 remaining conditions on the second block. So if you can satisfy almost all these conditions very quickly in a deterministic way. So if you can't satisfy those last conditions and you need them, they are necessary. You need to satisfy them to follow the differential path. And if you let them just be randomly flipped, those last conditions, every condition is true or false, so it's a binary value. How many trials do you need if you're just randomly flipping 37 bits before they're all 1s, they're all satisfied? You've got 37 true-false values, and they're all random. How many times? What are the odds that a 37-bit string chosen at random is all 1s? 1 and 2 to the 37. And the expected number of trials, 2 to the 37. So it's about 2 to the 37 work before you actually get all of these conditions probabilistically satisfied. Analogously, 2 to the 30 work to get all of the second block conditions satisfied. Okay? Is 2 to the 37 a big number or a small number? I ask a room of computer scientists. A number theorist would say everything's infinitesimally small that you write down, right? If an inner loop is somewhat simple, can you run 2 to the 37 iterations on a computer in 2006? Yeah, it's well within the range of what you can do. Okay, so using an IBM 690 computer, which is a very powerful computer, not what you're going to find in my laptop here, it took an hour, about an hour, to get the first block found. In other words, to satisfy those last 37 conditions. And then for the second one, only 2 to the 30 work is needed, so it's 128 times simpler. About 15 seconds to 5 minutes to find suitable M2. So in a little over an hour, she can find collisions this way. Okay, satisfying all those, most of the conditions deterministically, and then flipping bits for a while until the rest of the conditions are satisfied. I'm leaving out a lot of details here, but okay. Since then, people have been working on follow-up research related to Wong's attack. The first to produce anything was a guy named Vlastimil Klima, and he improved the attack down to 2 to the 33 for the first block, 2 to the 24 for the second block. And then I, with a couple of students last year, which just appeared last month in FSC, got the first block down to 2 to the 30, and we also implemented the attacks. So if you wish, you can go to my webpage and you can actually download the MD5 toolkit, which is supposed to be a platform for doing further research, testing. You can generate your own collisions yourself, and believe me, it is great fun. So you should definitely try it. Also, there is a full version of the paper, which you can find also on my website, that goes on for 39 pages about all these details that I've left out, because that's also great fun. Okay. The latest things, this is a very fast-moving area, as you might expect. Since we published our results just last month, 2 other groups are now coming up with even faster implementations. The 2 typical ways to get things to go faster: 1, improve the algorithm, and 2, throw hardware at it. So HashClash is a project in the Netherlands right now that throws hardware at the problem. They use highly parallelized attacks because these things are very parallel. Those 2 to the 37 trials, you can run them all at the same time if you have 2 to the 37 computers, or appropriately proportioned. This project, they've generated millions of MD5 collisions. They start generating them to order, like if you have a specific first block you'd really prefer, then using birthday phenomena can generate this chosen second block, a random second block. And then Klima has now come up with a new technique he calls tunneling. I haven't looked at yet, but he claims that it is much, much faster, and he has an implementation that runs in 17 seconds. That was posted to a mailing list last night at 1 o'clock in the morning, so fresh off the presses. Both groups are saying they can produce collisions in less than a minute now. So that's, we were at 5 minutes, and they're now much faster. But like I said, all of the research really has been focused on just speeding up the existing attack by adding conditions, but not by understanding differential. Okay, so what does all this mean? MD5, you can now find garbage 1 and garbage 2, and they hash to the same thing. Is it time to throw MD5 out? Does that lead to anything interesting? Does that lead to attacks? One thing I can't do is I can't take a contract that you've signed that was signed using MD5 and come up with another contract that says you promised to be my personal butler for 5 years and get the hash to collide there so it looks like you signed the different document. We don't know how to do that. That was our second preimage resistance. All we can do is get 2 blocks of garbage to collide. Can we do anything with that kind of an attack? It's definitely of theoretical interest, and it adds fuel to the fire of those who say that MD5 should be retired. All right, so there are some kind of tricks you can pull in order to get things to collide in an interesting way, and they are tricks, and I'll explain why in a minute. So here's a result from our paper from last month. We can make 2 distinct Linux binaries collide. So here they are. I run a program called B1, binary 1. It says hello world. B2, you run it, it says erasing your hard disk, please wait. Okay, so these are definitely different binaries because you run them in the same environment twice and you get 2 different results. And here's the MD5 of B1 and B2. They're exactly the same hash. How can you do that? It doesn't seem like it should follow immediately from the collision we just discussed, which was just 2 blocks of garbage. Okay, well, it's using a trick. So if you know what binaries look like on Linux or ELF or almost any platform, they typically start out with a text segment, which is the program code, and then have a data segment. And here the data segment is different. In the data segment, there's a 1024-bit chunk that is distinct within those 2. And in fact, they're distinct in exactly 6 bits, our usual friends, those 6 bits that matter for an MD5 collision. And they're generated using the proper chaining value if you hash the program down to that point. And then it's an MD5 collision carefully placed into the data segment. Okay? Everybody with me? Okay. So these 2 things will hash to the same value. But now why do they run differently? Anybody want to take a guess how you would get B1 to run different from B2 now that you've got these 2 programs?
Because the CD doesn't matter, right?
The chaining value doesn't matter. You can find a collision for any. So we actually, when you do this attack, you actually have to compute the chaining value down to the start where the collision is, generate a collision for that chaining value, and then plug them in. What do you mean you can do anything you want?
Well, you can do a lot more than using the chaining value being the same. That's crucial. Not having to be the same.
You can have one program that looks at one bit in the data and then does
behaves differently.
One thing or the other.
That's it. That's exactly it. So the program, because it executes, can actually look at the data segment and say, let's look at the 19th byte, the high bit. And it happens that the 19th byte will vary in an MD5 collision. And you say, well, if the high bit's set, say hello world. Otherwise, say erasing your hard disk. So behave differently depending on if you're in the binary 1 where there's a certain, the first piece of garbage, or in binary 2 with the second piece of garbage. You can follow that. You just look at yourself and behave differently based on which version you are. But yet the two binaries will have the same hash value. So the reason that this is ridiculous in some way is because if you tried to pull this, well, let's do the next example, which is more interesting and uses the same trick. This is by Marcus Daum and Stefan Lux, and they use the same technique, and it's their technique. So they did it first. I should make that clear. They had two PostScript documents that collide. That's a bit more interesting, right? You look at one document, and it says one thing. It says, I don't know, I pledge to pay $500 a month in rent. The other one says, I'll be your butler for a year. And it looks like you've signed one when actually they're claiming you signed the other. And here it works the same way as the previous example. It turns out PostScript is a programming language. Did you know that? PostScript actually is a programming language. So you can do the same exact thing. You embed a collision somewhere in a PostScript document, and then using the PostScript programming language, you see which document you are. If you're in the first case, you output, I promise to pay my rent. In the second case, I promise to be John's butler. Okay? So now, you sign the first one that says you'll pay your rent, and then I could go take you to court and say, look, you're supposed to be my butler. It's right here, and I've got a digital signature, and it's all good. Why is this fishy? Why would this not hold up in court? Yeah. You look at the PostScript source, and you say, wait, there are two different documents embedded in here, and a program that's selecting one based on some weird bit down lower, right? That's pretty fishy, and I think that anybody with the amount of technical sophistication, especially knowing of this attack, would immediately say, you've been duped, and you clearly signed one version or the other of this document, but we're not going to claim it was one or the other because it could have been either one. Nonetheless, this is kind of an interesting trick, and people thought it was quite amusing and maybe even important. Another example is Lenstra and De Weger showed that you can get two X509 certificates to collide. Basically, they put an MD5 collision in the first 1024 bits of the modulus, and then randomly generate the last one so that they get a proper RSA modulus that differs in those 6 bits. It turns out you can generate two moduli that differ in specified bit positions, and this is a known result from a couple of years ago. I'll skip the last details here, given that we have only a minute left. So finally, to wrap up, MD5 now has millions of collisions known against it. SHA-1 has none known. However, Zhaoyun Wang is now working on SHA-1, published a paper last year getting the 2 to the 80 expected value down to 2 to the 73, and now her latest results say 2 to the 63 work. 2 to the 63 is a big number, but it's within the realm of parallelized attack. If we had enough computers, we could probably do this. No one's implemented her method yet, so there's still no collision known. And it may be the case, sometimes the analysis estimates are wrong for attacks. The NSA likes to say attacks never get any worse, they only get better. But sometimes they do get worse when it turns out, like it did with AES a couple years ago, when the world sky was falling and it turned out the attack analysis was really far off. So who knows? We may be hearing about a SHA-1 collision next month, and we may not hear about it for 3 years. There, of course, are also people in the research community who are scrambling to find new hash functions. You may have heard of SHA-256. Whirlpool outputs 512 bits. The very smooth hash is a technique used by Contini, Lenstra, and Steinfeld, which uses properties of number theory that says if you can find a collision, you can actually efficiently factor, which seems like something we feel secure sleeping at night. And there's some old algebraic hashing that's very slow that Domcore created. So there are new efforts to produce new hash functions, oftentimes using completely different approaches, so that the attacks that Xiaoyun Wang has been mounting won't apply to them. In fact, if you'd like to sleep well at night, you may want something that says, if you find a collision, then something really hard problem is going to be solved, and that may give you more assurance. Okay, I'll stop there and take any questions you might have. Yeah. That's correct. Yeah. So the question was, for SHA-1, it's 2 to the 63 work to satisfy all the conditions. That's right. And as you improve the list of conditions that you can satisfy deterministically, that number keeps going down. Right. So if you go to the HashClash website, it started out just being, let's throw a bunch of parallel computers at MD5 and see how fast we can go. Now they're under a minute. Then they started doing custom tailored collisions because we can generate collisions so quickly now. Let's try to create collisions of a certain form. They state on their webpage that they're interested in SHA-1 as well, but they haven't begun working on it. It would be interesting for somebody with big iron to go after this and just to see experimentally if this result can be realized in the complexity that was estimated by Wang et al. Wang, Yao, and Yao, I think, are the people working on this currently. Hmm?
So what do those 30 conditions look like? Do they say the relationship between this and wrong?
Yeah, they're all...
How can you efficiently, because you search all the 30 possibilities, but you enumerate all the scripted.
Okay. So all of the conditions, the 290 conditions and 310 conditions, they all look like something very simple, like this step value, the 22nd bit must be a 1. This step value, the 32nd bit, 14th bit, must be the complement of the 15th bit 2 steps before. Things like this, but just this must match that, this must match that, okay. So you can deterministically satisfy those conditions by just flipping bits until they're all true. Now the problem is that if you recall, in the first round we use all 16 chunks from the message. Second round, we recycle and use them all again. Third round again, fourth round again. So if you're down in the third round and you start mucking with the bits of the message, you're going to start violating the conditions you've already satisfied. You're going to unsatisfy them. So you can't manipulate these things without an algorithm that cleverly changes not only this bit, but this one, this one, this one, and keeps all those conditions satisfied that were satisfied before, because you're going to shoot yourself in the foot. So we don't exhaustively search on the last conditions. What we do is we randomly generate new attempts, new bits that still satisfy everything that we've got, all but the last 30. And then the last 30 bits are all essentially random. And the chances that a random set of 30 bits will all be ones, all the conditions will be true, is about 1 and 2 to the 30. So it takes 2 to the 30 trials. So basically, we do an algorithm that satisfies all but the last 30, and the last 30 are just a throw of the dice. And eventually, you get them all to be true. And then you satisfied all the conditions for block 1. You do the same thing for block 2. And then you usually get a collision. It's actually not a set of sufficient conditions. It's just almost sufficient. Anything else? Yeah. You know, I don't know offhand. It's once again very close, but I don't know what the differential is offhand. It's yeah, exactly. It's unclear whether she doesn't know how she does it or she'd rather not talk about how she does it. And you know, I'm all for the approach of I'd rather not divulge my methods right now. I'm still busy attacking these things, and you know, when I'm done, maybe I'll sit down and try to write down a methodology of the approach. But at this point, you know, garner as many new results as you can using your methods. So, at the same time, other people are trying to figure it out, but shrouded in mystery still. Yeah.
Back to flipping the special bits in a binary. If somebody either designed a program maliciously or found one that by chance they could flip this bit and make it do something mean, how could you use that maliciously if it only produces the same MD5 sum? Like, is there a security threat at all there?
Yeah, so you can imagine a setting where perhaps, and this happens, for instance, in the state of Nevada, goes into their slot machines and does an MD5 checksum on the ROMs to make sure they haven't been tampered with. Now, why do you think the state of Nevada is concerned with tampering with slot machines? Sorry? Yeah, no. This is the machine. This is the ROM that has a program that computes whether the machine pays off or not. Now, who do you think could realistically tamper with these things? Somebody who wants to pay off. I mean, like a customer who walks in off the street and then, with 10,000 cameras, opens the slot machine door, replaces the ROM with one of his own choosing? Unlikely. What? Yeah, the casino people, right? The casino people would like it to pay off less often. And so, in order to keep the casinos honest, the gaming authority goes in and checks the ROMs to make sure that they haven't been tampered with by the casino. You as a patron, you couldn't even open the door without 6 guns on your head within 2 seconds, right? The people watching you constantly, but the people who work there have access to these machines. So they hash the contents of the ROM and check it against a list and make sure that it hasn't been changed. And this is Chimera by hash. Okay. So let's say now that you've got 2 programs that have the same hash. One behaves one way, one behaves another way. Wouldn't it be lovely to be able to install one, have it check according to some hash value, and then later on go and put a new ROM in that actually pays off less? But when the gaming authority does the hash, it's undetected. So there's an example where you might be able to, have a program execute faithfully in one case and then have the same hash later execute unfaithfully. Anything else? All right, well, thanks for your attention.